Great. I think we can get started. Thank you everyone for being here. It's great to see you all and to welcome Cayman Unterborn, who joins us today to continue our Rocky Worlds discussion series. Just before we start, a quick reminder of netiquette. Please use your full name and keep muted throughout the talk. If you're asking a question at the end, if it is possible, it would be great if you could turn on your video as well. I will now hand over to Cayman to talk to us about is this planet rocky? Precision requirements for robust small planet classification. Thank you so much and take it away.
Unmute. Thank you. All right, let me share my screen. All right, do you see just my slides? Cool. All right, well, thank you very much for having me. This talk I'm going to present today is a little bit different from the abstract I submitted. I wanted to add in some stuff about TRAPPIST-1. So I'll just get started right here with what is TRAPPIST-1. So TRAPPIST-1 is a system of 7 planets. They all orbit within the orbit of Mercury to compare it to our solar system. They orbit an M-dwarf. And if you work in exoplanets at all, you've heard of TRAPPIST-1. It is the poster child for an exoplanetary system. And so the first part of this talk, I want to go into putting TRAPPIST-1 in context and then discuss how it's kind of warped our view of habitability. So one of the reasons TRAPPIST-1 is so exciting is that if you were to compare, this is on the x-axis is the illumination from the star. You can just think of it as distance. And then the planet density relative to the Earth on the y-axis. You can see that most of these planets have Earth-like densities. And perhaps more importantly, at least planets E, F, G, TRAPPIST-1, E, F, and G are all within the habitable zone of the M-dwarf TRAPPIST-1. So in some sense, when we discovered TRAPPIST-1, I don't know, it's been about 10 years now, it was super exciting because we just found a whole solar system with some planets in the habitable zone, and it's gotten a lot of hype. I actually tried to quantify the amount of hype for TRAPPIST-1. So this is maybe 2 or 3 months old now. But I went through the NASA ADS abstracts, just searched TRAPPIST-1 and pulled all the refereed papers. And back then it was 145 papers with 9,000 citations. The TRAPPIST-1 system is very cool in the exoplanet literature. Everybody loves to write a paper about TRAPPIST-1. And if you were to look at what those papers talk about, there's things like observation and characterization, just trying to understand the TRAPPIST-1 system. M-dwarf physics is a big one. I'll show you in a little bit about just why TRAPPIST-1 M-dwarf physics are important. Atmospheric chemistry is certainly something, especially if we want to know if there's atmospheres on the planets in the habitable zone. Just because you're in the habitable zone doesn't mean you're habitable. But they're with 3 planets potentially in TRAPPIST-1's habitable zone. They're very exciting. We want to get atmospheres for them. And finally, of course, is habitability. And this is the one that a lot of people have spent a lot of time talking about. So I wanted to sort of say why there are so many papers. And the first thing I need to introduce to you is this concept I came up with a few years ago called the Nominally Rocky Planet Zone. And this is on the plot here, we have density of the planet on the y-axis and the radius of the planet. This is just a different way of looking at what's called a mass radius diagram. And the NRPZ, the Nominally Rocky Planet Zone, are the range of densities you would predict if you used stellar abundances as a proxy for planet abundances. Now, that may not be quite 1-to-1, but it's a good starting point to say, like, planets within this blue band here have densities that are characteristic of being a planet with only an iron core, a silicate mantle, and a thin atmosphere. And that's what I'll call a rocky planet. On this plot, the TRAPPIST-1 planets are plotted in red, and every other planet below 2 Earth radii is plotted in gray. And one of the things that really quickly jumps out to you is the uncertainty in the mass and radius are almost as big as the size of the plot of the points themselves. They have extremely small uncertainties. And if you were to quantify what fraction of TRAPPIST-1 planets' mass or radius and density fall within the NRPZ, it's on the order of 90%. So this is a very well-constrained system. And the mass error bar is on the order of less than 5%, the radius are less than 2%. So keep those numbers in mind because they'll come up later in the talk when I start talking about precisions. Just a different way of looking at this. So here are histograms of the total error in radius and the total error in mass for a few different kinds of planets. And it's really clear to see the peak, that's the average of TRAPPIST-1, all fall well below everything else. So something about TRAPPIST-1 made it such that we can get absurdly low error bars. And those reasons are kind of twofold. One is that it has, TRAPPIST-1 was observed to have transit time variations. I won't go into what that is, but it's a special case of astronomy, especially in exoplanet detection. And because they are in such tight orbits, they have mean motion resonances, and this allows a lot of the uncertainties to sort of drop out. And so you can get extremely low error bars for the TRAPPIST-1 planet. Oops. So another important thing about TRAPPIST-1 is that it is observable. This equation up here is called the transmission spectroscopy metric. This is Eliza Kempton came up with this in 2018, and it's sort of if your planet, things like the radius and mass of the planet, the equilibrium temperature, the radius of the star, and its brightness all go into this TSM term. And essentially what it tells you, it's a proxy for the signal to noise. So the higher the TSM, the more signal to noise you can get with something like JWST. And anything above 10 is good, or is considered good enough signal to noise for JWST. Write a proposal. Hopefully you get some time. The TRAPPIST-1 planets all have a TSM between 12 and 30. So TRAPPIST-1 just by itself is very observable. So most things that are observable get observed. Oh, and that's what I just said. Yeah, good signal to noise. But let's break down each term in the TSM and see how TRAPPIST-1 looks compared to the rest of the exoplanet sample. So first, from the next few plots, the y-axis will always be the transmission spectroscopy metric. Again, above 10 is good. And I'll vary the x-axis. So this first one is brightness. So this is this MJ term. This is the magnitude in the J band, which is just an astronomy band, wavelength band. And it's really easy to see. And TRAPPIST-1 I plotted in red is actually one of the dimmest stars in our system. I know it looks like it's a higher number, but magnitude space, lower numbers is better. Lower numbers is brighter, excuse me. Higher numbers are dimmer. So TRAPPIST-1 over here is actually not that bright. It's very dim compared to the rest of the exoplanet sample. Next up is the stellar radius, which goes into the denominator right there. It has the lowest stellar radius. Now that's actually pretty good because it's in the denominator. So lower radius means higher TSM, but it's actually the lowest in terms of stellar radius. Everything else is bigger. Next up is the stellar effective temperature. This goes into the T equilibrium term, but it actually, TRAPPIST-1 orbits some of the coolest stars. In fact, for this, that would actually lower your TSM if you're around a cooler star. Oh, wait, no, I take that back. Other way around. It increases your TSM. But you can see TRAPPIST-1 is absolutely unique compared to the rest of our sample. If you care about habitability, you really care about one thing, and that is, not one thing, but a very important thing is the equilibrium temperature of your planet. And here again, you can see TRAPPIST-1 have some of the lowest equilibrium temperatures. It's important too, when you look at the rest of the sample, most of them are hotter. And I've plotted here on this vertical line, the dry peridotite melting point. We have many planets that are so much hotter, so hot, in fact, that rock might melt. So TRAPPIST-1, if you care about habitability and cool conditions conducive to habitability, lower equilibrium temperatures is better, and TRAPPIST-1 has some of the lowest. Next up is one thing you would care about with observations is how many times it orbits the host star while you're looking at it. If you have a shorter period, you can get more observations of the same planet in a shorter amount of time. Here I've plotted semi-major axis as kind of a proxy for period, but it's okay. The point here is that TRAPPIST-1 falls kind of in the middle. So in terms of density, they're not that impressive. Oh, in terms of the orbital period. And then with planet density too, we have, it's just kind of in the middle. But so TRAPPIST-1 has a lot of good things going for it. It's observable. The TSM's above 10. You've got 7 planets to work with. Great. Oh, well, this is everything else. If you were, I can come back to this figure later, but that's everything all at once. But the key point is that for some important terms, TRAPPIST-1 is clearly an outlier relative to our data set. So did I skip something? No, I didn't. Okay. So let's say you wanted to study a rocky planet. If you wanted to study a rocky planet, you need to be able to classify it as rocky. And to do this, you would quantify what's its likelihood of being within the NRPZ. And so of the 114 planets with good TSM and mass and radius available, 8 have an NRPZ high enough to be considered rocky. 6 of those are TRAPPIST-1. If you lower this threshold a little bit more, you get a lot more planets that are not have a very low probability of being within the blue band, and thus we would call them not rocky planets. But if you're looking for rocky, TRAPPIST-1 is the only game in town. It's the only one with the uncertainties low enough. If you care about cool planets, 6 of them have equilibrium temperatures less than 300 K. Most of them are TRAPPIST-1. Even the medium hot thing going from 300 to 500 Kelvin, TRAPPIST-1 are still in there. But essentially, in our sample, if you care about habitability and you care about equilibrium temperature, only TRAPPIST-1 and a few other planets meet this criteria at all. And again, a lot of them are well above 1300 Kelvin and are melting the rocks. If you care about transiting planets, you can look at this and say, well, if I want a lot of transits, well, these are the ones with less than 1 day. But again, TRAPPIST-1's in there at these longer periods. Ideally, if you wanted to think about cool planets versus often transiting planets, those with a shorter period are going to be hotter. They're going to be closer to their host star. So you want to push this out a little bit, preferably where the TRAPPIST-1s are, which are these kind of middle zones. Higher periods would be great. Yeah, TRAPPIST-1 is a great example, but we also have many more planets that meet that criteria too. So ideally, you would want all 3. You would want a bright star to look at, a cool equilibrium temperature, and you want it to transit a lot so you can get many observations. So the 114 planets with mass, radius, and TSM, only TRAPPIST-1 meets the conditions of being rocky and maybe habitable. That's it. Those are the only one that meet all those criteria. And so here I've plotted equilibrium temperature versus brightness, and then the colors here represent the orbital period. So if you want a short period bright thing, maybe you look at that one, maybe you look at that one. But the problem is that TRAPPIST-1 makes us kind of biases us towards one system because it's the only system that meets all the criteria for maybe being rocky and maybe being habitable. We have many brighter, hotter, shorter period planets in our sample, but we don't really honestly spend a lot of time talking about them because TRAPPIST-1 kind of sucks up all the oxygen. Yeah, okay, I'll move on to the next one. So like I've said before, TRAPPIST-1 is observable and interesting. They're short period. Their transit timing variations and mean motion resonance gives us extremely low uncertainties in mass and radius, which allows us to classify them as rocky, and they're cool. So TRAPPIST-1 is observable. That's probably the main reason why so many papers get written about it. But that does not mean it's good for habitability. Just because TRAPPIST-1 are rocky planets and some of them are in the habitable zone does not mean that other aspects of TRAPPIST-1 make it less likely to be habitable. So some work we did back in 2022 was showing that because TRAPPIST-1 is very old, it's over 8 gigayears old compared to the Earth, it shouldn't be very geologically active, and in fact, it would struggle to retain an atmosphere, at least volcanic. It will struggle to support volcanism anymore. It's just so old; it's run out of power. Another important one is that no thick atmospheres were found for B, C, D, and E, TRAPPIST-1, B, C, D, and E. And we use that fact to say, well, actually, it's probably that TRAPPIST-1, at least B, maybe C, formed in a volatile poor environment. Otherwise, we should see an atmosphere today. So that's a really cool paper. I'd highly recommend it if you're curious about TRAPPIST-1 habitability or a lack thereof. Of course, TRAPPIST-1 is an M dwarf, so it's a fairly active star. But so the main point here is that TRAPPIST-1 kind of skews our thinking about what we need to be a habitable planet. Do we really need error bars low? Does temperature matter? And lots of other questions. But in some sense, TRAPPIST-1 is an outlier. And it's kind of amazing we found it at all because it's, again, around a very dim star and has other problems going with it. So you may say, let's go find more TRAPPIST-1s. It seems like, well, TRAPPIST-1 itself may not be great for habitability. If we find more planets with TTV and mean motion resonances, that would be great. So this is the only wall of text I'll have in the talk, but I want to sort of break it down that why it's so amazing that we found TRAPPIST-1. So for any given planet, the geometric probability of a transit happening is low. So that means we're looking from Earth or from space, we're staring at a star and we see a transit. The odds of that happening are very low. You need TTVs, transit time invariations. That lowers the probability more of finding one. And then mean motion resonances to get the error bars down lowers the probability even more. And so you find a TRAPPIST-2, say, and you just hope that they're rocky and in the habitable zone. So you would spend a lot of time hunting for these things, and then you just have to get lucky that they are rocky and in the habitable zone. So TRAPPIST-1, in some sense, kind of warps our thinking of habitability because it's a rare system. The odds of us getting they're rare to find, and we have lucky that they're even Earth size. But there's certainly more important. There are many other stars out there with planets that may be just as interesting as TRAPPIST-1, but don't get a lot of the resources. So what can we do? Here I've plotted this radius density, and then the sort of observability, the brightness versus equilibrium temperature, and things like that. What can we do? So one of the big problems is TRAPPIST-1 has small error bars, which allow us to classify it. The majority of these planets, if you look at the gray points here, have error bars that are huge. And so classifying whether they fall in the Nominally Rocky Planet Zone is actually very hard because their probabilities of being in that zone are low because they have high error bars. So first thing we need to do is get error bars to classify a planet. And we can do this by getting more transits or using these new instruments that are coming online called extreme precision radial velocity, which will help us maybe pin down the masses and radii of these planets. And another important thing is if you care about habitability, we don't have very many planets that are cool. Cool in terms of temperature. They're all cool. And so most planets are too hot to be habitable. So you have this twofold thing of the observations say we can't really classify this planet as rocky. It's just as likely to be a water world or a Mini-Neptune. But they're also so hot they might melt rock. So those are definitely not really planets you want to look at for habitability purpose. Yeah, most planets. So this is kind of the sum up figure of the first half of this talk. So here I've sort of, what happened? There we go. What I plotted here is equilibrium temperature versus average density. You don't need to worry about what the shapes mean necessarily. We'll just look at this more generally. But if you think about trying to classify a planet or try to figure out which ones are more important to go after for observations with, say, James Webb Space Telescope, average density is sort of a proxy for what kind of planet are you. You can see that these low density things are maybe Mini-Neptunes or water worlds. Things in the gray or high density relative to Earth and could be considered Super-Mercuries. And you kind of have this intermediate zone right here, this green and orange. Green is, these are cool planets that have densities such that we can probably say they're rocky. The TRAPPIST-1 planets live in this green zone. And in the orange, these things are hotter and of intermediate density. But in some sense, these are the planets we care about. These are the especially the ones in the green, because those are going to be at least maybe potentially have conditions favorable for habitability. But yeah, something about them isn't right. Whereas those in the pink over here, these are already hotter than the melting point of rock. You probably don't want to, if you're writing a proposal and you're using habitability, you probably don't want to use these very hot planets as your case. So yeah, and then I'll come back to this atmospheric characterization in a little bit later. All right, so I mentioned earlier that error bars are a very big problem, and so now I'll switch to, well, how do we classify exoplanets? So yeah, so we looked at 37 planets. These are planets that were chosen because they orbit bright stars. Brightness is, the lower the brightness, or the more bright a target is, the faster you can get data. So in this sense, we looked at 37 planets that have visual magnitudes less than 11. And where we wanted to look at the lower equilibrium temperature stars. So we limited ourselves to those below the melting temperature of rock. And yeah, so if you care about the visual magnitude, there you go, distance. You can see they kind of clump up in density, and they're all periods, not too bad. There's some longer period stuff. But over here, this is your mass radius diagram. This is the one we'll spend a lot of time looking at. And you can see I've plotted the NRPZ here as this gray dashed band. So if your average is within the NRPZ, there's a decent chance you could be rocky, but we got to quantify that. If you're outside of the NRPZ, even with big error bars, you can see we've got maybe this population up here. We've got some of these stragglers down at the bottom that might be Super-Mercuries, but you can see the error bars are quite big. So what Stephen Kane, my colleague, and I basically wanted to build on from this previous work is how can we classify these planets within this orange zone in order to better classify them. So, oh, there we go. I just went into this. Just so you know, 31 of the 37 planets in our sample have TSM high enough and good enough for JWST. The average percentage of data, of all data that's in the Nominally Rocky Planet Zone, is 37%. So pretty low. We wouldn't call that rocky, but that's mainly because the error bars are kind of killing us. They're too big. So what Stephen and I did was we asked the question, how low do we need to make the uncertainty in mass and the uncertainty in radius in order to classify a planet? And so essentially what we did is we simulated new measurements at arbitrarily low uncertainties. So here I'll show an example for a planet LTT 445 AC, and the ellipses here are its original uncertainty. So you can see that a lot of the data for this planet falls outside the NRPZ just at its current uncertainties. And what we did is we would essentially assume a new measurement can change the average values of M average and the mass and radius. And we asked, as you lower uncertainty, how does the fraction of models that fall within the NRPZ, how does it change? So you can see at 75% uncertainty over here that I choose a new average. So that's why the points bounce around all over the place. And then I count up how many of those models fall within the NRPZ following this equation. It's very simple. It's just for a new measurement at a given uncertainty, the number that are within the NRPZ divided by the total number. So at 75% of the current uncertainty, you can see a few still populate within the NRPZ, but there's still some outliers. And because the error bars are so big, it lowers its probability. I'll show you a figure in a second. If you make uncertainties extremely small, now you can fall within the NRPZ and still get extremely high. I'm just going to show the next figure. Yeah. So you can look at the cumulative distribution of these things and see how it changes. So in the red is 75% current uncertainties. You can see that when you run this model, the total number of models, 21% of all models fall within the lowest bin, which we call not rocky. Low NRPZ means not rocky. That would be like this point way out here has a very low NRPZ. Then you get about 75 or 80% in your inconclusive zone, and nothing in the rocky, the very high NRPZ zone. For once you start lowering uncertainties, you can see it become much more bimodal, where some amount, a larger percentage of models fall outside of the NRPZ, while it increasing the amount that fall within. So essentially what we're doing is we're lowering the uncertainty and trying to turn this more into a bimodal distribution. And that bimodal distribution will tell us the likelihood of a planet being rocky or not rocky. And I'll give you the classification scheme. So there's four basic ways, four basic kinds of planets you can have. So if we basically say once 75% of all models fall within either the rocky bin, we would call that a rocky planet. If 75% of all models fall within the not rocky bin, not rocky. But you can see for this planet, even at 20% lower uncertainties, neither of them reach that 75% threshold, but that does not mean it's not classifiable. The sum of those two bins adds up to 85%. And so, adds up to 85%. And so we would call this a classifiable planet. We just can't tell you what it is until you actually measure it. And so there's two different kinds of classification. One, if the majority of models fall within the rocky bin, we call that a leans rocky planet. If the majority of models fall in the not rocky bin, we call that a leans not rocky. So as we drop uncertainties, we can see how the spread changes and count which bin has the most, and we can go from there, and we call that a classification. So when you run this for all of these planets, we have sort of four basic things fill out. We have 12 planets in our sample that are currently classifiable. Even with their error bars being very big, we can definitively say there are 4 Super-Mercuries, which are here in gray, and 8 Mini-Neptunes, which are up here at the top in red. 8 are confirmable as not rocky once you lower the uncertainties, and those are shown in pink. So these pink points, if uncertainties got low enough, and I'll show you exactly how much in a second, you could probably confirm them as not rocky. And the rest of our planets in our sample fall into the leans rocky, which is in blue, and leans not rocky in the orange. So I'm not going to spend too much time on this, but essentially we're able to come up with 4 different classifications for these planets as the uncertainties get low. And now I'll start talking about how small the uncertainties are going to be. So let's look first at these Mini-Neptunes up here. And so here are contours. So this is our modeled uncertainty in mass and our modeled uncertainty in radius. And this is the fraction of models that fall in the rocky bin and the not rocky bin, and then the sum of the two if there's no, but excuse me. For this planet, even at a mass uncertainty of 60%, so this is its current uncertainty, lower, even having that even if you halved the uncertainty in mass, you would still produce 90% of all models would fall in the not rocky bin. So at this point, lower uncertainties aren't going to help you. It's already a not rocky planet, and this is something the NRPZ is very good at, which is finding planets that are not rocky. But I won't spend too much time on this. I want to look at the next one, which is a confirmable not rocky planet. So if error bars go down, you can classify them a bit better, or you can classify. You can see their current error bars at 1.6 and 0.05. At low uncertainties, so this is a sigma m of 0.5, so almost a very big drop in mass error bars. Only about 5% of models would produce a rocky outcome, whereas 75% would produce a not rocky outcome. And so that's why we classify this as a not rocky planet with lower uncertainties. But if you care about, there's a typo there, that should be R naught. You can see that, in fact, that's a typo. You can see that mass error bars especially have to be almost halved to a third of what they are now in order to reach this 75% threshold, which is arbitrary, but it's where we started. Next up, we're going to look at this orange one right here. So you can see it's right on the edge of the NRPZ. So this is a Leans not rocky exoplanet. And in this case, at lower uncertainties, as you start dropping the uncertainties in both mass and radius, 15% of models become rocky, whereas 60% of them at this uncertainty that I marked fall within the not rocky. So it has some probability of being rocky when you measure it again, but it's not a very high percentage. But unlike the previous two, only the sum of the two adds up to 75%. And so you're going to have to lower uncertainties by at probably half in mass and almost over half in radius in order to classify this planet. Now, that may not sound like a lot, but in a few minutes, I'm going to quantify exactly how massive of a jump that is for exoplanets. All right, last one. Oops, I go backwards. Yeah, I went backwards. Oh yeah, so yeah, I won't read that. Last one is this blue one right here. This is a lean rocky exoplanet. It's going to look extremely similar to the last one. Oops. There we go. It's going to look extremely similar to the last one. So in this case, as the uncertainties go down, the percentage of rocky goes up, percentage of models in the rocky bin goes up. So about 60%, if you, let's see, 0.32. So this is again about a halving of the uncertainty. If you have the uncertainty in mass and quite a bit of a drop in radius uncertainty, you can get about 60% of models to fall within the rocky bin and about 15% to fall into the not rocky bin. So yeah, this is, but we can classify this as a leans rocky exoplanet. So yeah, so at the uncertainties, we choose 60% chance of being rocky, 15% of being not rocky, and 25% of being inconclusive. What's important, though, is that if you were to take a new measurement at these uncertainties, it would be enough to classify them as one or the other. This is kind of the probability of your measurement being not rocky and your probability of the measurement being rocky, and there will be sufficient uncertainty to distinguish between the two. So here's everything all at once. So this is the current NRPZ percent. So this is using its error bars as they are now. And then on the y-axis is the uncertainty in mass needed to classify and the uncertainty in radius to classify. And I've broken these up by the different classifications. But essentially what we can take away from this is in terms of mass uncertainty, the confirmable not rocky exoplanets need to go from 30% average uncertainties down to 7. And as the your original NRPZ increases, and this is how likely you would be in the nominally rocky planet zone, the uncertainties you need get lower and lower and lower. So we need very stringent mass uncertainties and radius uncertainties in order to classify these planets. And in fact, as far as I know, this hasn't really been quantified in this way relative to the NRPZ especially. But essentially, there's sort of a 1/x here. The higher your current NRPZ is, the smaller your error bars need to be in order to classify that planet. And in some cases, it's halving. And that may not sound like a lot, but I'm going to show in the next slide, that's a lot. So you can ask the question, how long will it take you to achieve that level of uncertainty? I'm going to skip the first two and just go right over to the period. Or I'll talk about this actually first. So in the middle figure, this is the average mass uncertainty you need to classify divided by the number of orbits. So this is how often it's orbiting its star, and so every time it orbits, you get an observation. But you can see that for the majority of our planets, they need uncertainties between 2 and 6% in mass, and it's going to take you between 10 and 100 orbits to make that happen. Now, orbits is not what I usually think in. I think in terms of time. So if we go over to the next one, this is the number of orbits times the period in days. And you can see some of these planets will take between a month and 6 months of constant observation. And there's even ones that will take longer than a year. So this equation is basically the number of nights is equivalent to the uncertainty in your instrument divided by the RV amplitude and the mass you want to achieve. So yeah, it's even worse when you look at radius, and I won't go too in depth in this figure, but we can see on the bottom two panels, on the bottom two panels, you can see as, again, you need 1 to 3% uncertainties in radius. This is going to take you between 10 and 10,000 plus days, or orbits, excuse me. So you can get the error bars down this low. It's just going to take forever. And in fact, that may not be a feasible amount of time to dedicate to looking at one planet. So here again, I've marked the different, so 1 month, 6 months, 1 year. Some of them would take up to 5 years of continuous observation to get the error bars down that low to be able to classify them. And I think that's an important point that hasn't been really thought of, is how long it will take you to actually do this. So this is now I've plotted on the y-axis here. So this is the amount of time needed to achieve the radius uncertainty and the time to achieve the mass uncertainty relative to each other. And it's important, in order to classify these things, you have to measure both the uncertainty in radius and the uncertainty in mass. Oh, there's another typo. In order to classify them. You can't do just one, you have to do both. This does assume continuous observation, so that's important too. Are you going to be staring at the same planet for a year? Probably not. Our treatment of error doesn't account for all the many observational uncertainties, so these are probably lower limits on the amount of time it would take. And so the basic takeaway of this part of the talk is that while we can classify planets with mass radius, it's going to take probably too much time. So I worked on mass radius models for my entire career, and I wrote this paper and realized I may have put myself out of a job because the mass radius models just are not going to be good enough in a reasonable amount of time in order to do this. So what do? I have a thought on how you can prove something is rocky. And the way you prove something is rocky is to go look and see if there's an atmosphere there. If there's a thick atmosphere, that is not a rocky planet. That is a mini-Neptune. If you see water, that is a water world. So you can basically look for the presence or lack thereof of a thick atmosphere, and that will tell you instantly whether a planet is rocky. So that's sort of extending why I said these are ideal for atmospheric confirmation, because their densities and the uncertainties are such that we can't classify them with mass radius. But if you go get a simple atmospheric measurement, you might be able to tell something. And in fact, this has already been done with JWST. So I've highlighted the 5 planets here that I went through the literature and found had observations of their atmospheres either by Hubble or JWST and put some constraints on it. And those in black I've shown can have significant atmospheres, so TOI 36b and 260, and the ones in red have thin atmospheres. And you can see we could have maybe inferred that from mass radius, but it would take us on the order of almost 100 days for some of these planets, almost 1,000 days for some of these planets. And in fact, I've marked the ones in blue over here also have been observed by JWST. So this new atmospheric measurement does not have to be an in-depth, get every species involved. You really just need to tell me, for classification purposes, Is it hydrogen, helium? Is it water? Or is it a high mean molecular weight atmosphere? If those, you think of those as three different possibilities, that's all I need to know. And then I can much more easily classify it so that we spend our time looking at rocky planets and not looking at, if habitability is your goal, looking at rocky planets and not sort of oddball mini-Neptunes or water worlds or things like that. So here are my conclusions. I'm not going to read all of this, but I did want to highlight here. These are the remaining planets in our sample that have not had atmospheres observed. And you can see if you want to get atmospheres for these things, maybe HD 136352b is where you should start, because that's going to take almost 100,000 days to pin it down with mass radius uncertainty, are the ones you should go after. But this, I think, is a cool use of using mass radius modeling, using statistics to do better target selection and quantify how long it would take us with the instruments we're building to classify a planet. And I wrote this paper and I was very surprised that it's going to take a long time if we want to do it by mass radius. It doesn't mean we can't. It just means it may not be the best use of our time. Oh, one important thing I wanted to mention about these planets right here is, so you can see these would take on the order of, let's say, that's 1 year for that planet right there. If you look at the number of transits JWST needed to used in order to get their atmosphere, it was 5. So 5 orbits instead of, in this case, probably a couple hundred. So in this sense, JWST is just so much more efficient than anything else. And so if we can get atmospheres, simple atmosphere information, that will help us a lot. So I'll leave it there and thank you.
Thank you so much. And we have plenty of time for questions. Does anyone have a question to get us started?
Oops.
If not, I might jump in with one while people are still thinking. This is really cool, and I like your statistical approach here. I was wondering, for using the atmosphere for the classification, I guess there's some level of risk with, for example, if you have a hazy or cloudy atmosphere that gives you a flat line and it's hard to distinguish if it's hydrogen rich or not. Do you think that's something that would be interesting to fold in from a probabilistic point of view, based on like different temperature regimes, or like how do you think might be a way to tackle that issue?
Yeah, I think you're right. I think we need to understand what the flat curve means, and I think even think more broadly about just putting some. What I didn't really go into is defining what I think a rocky planet is. How thin of an atmosphere makes you rocky, and I guess I think of it compositionally. So if it's water that you see in your atmosphere, even though maybe it's flat, but you can maybe infer it's water, that's a water world. That's not rocky. Same thing if you see hydrogen, helium, that's going to tell you you're probably more on the mini-Neptune side of things than rocky. So honestly, the measurements I found best were the thermal observations that said, this is a bare rock. Bare rocks are great because that means it's a rocky planet. A bare rock doesn't mean completely bare, but it has a thin enough atmosphere. So I think you can certainly work it into these models, but we kind of need to have a bigger discussion of how much atmosphere is too much, and is habitability driving that conversation, or is observability driving that conversation? Because I'm of the mind that if you see a signal of water or hydrogen, helium, that means you already have too much to be kind of habitable. So you're almost looking for a null result.
Mm-hmm. Nice, thank you. I think Claire has a question. Go ahead.
Hi, Cayman. I'm really interested. So I'm wondering how the time to get the mass and radius precision compares to trying to observe any spectral signatures from a rocky crust directly.
Observing so how does it compare to what again? Say again, please.
If you, for example, are trying to observe any spectral signatures from the crust itself through some of these SIO features. I don't know very much about this, but I don't know, is that a possible way to say if a planet is rocky or not, or is that also observationally very challenging?
I don't know the observational challenges, but as playing the astronomer today, even though I'm a geologist, I would say you can I think that would be really good observation to tell you if something is rocky because you would see it. The only thing I would worry about is you'd probably be so hot you're not habitable. But that's okay. I think we need to know which planets are rocky and which ones aren't. And especially, I didn't really go into why, but if you're doing population studies, you're trying to understand the formation of rocky planets. You don't want to use a sample that might be clouded with water worlds or other intermediate density things that are not rocky. So yeah, I think any clever way you can figure out a planet is rocky is going to be great. It may not be habitable, but that's okay.
Thanks.
Okay, I think David was next.
Hey, Cayman. Long time no see.
Yeah, it's been a while. Thanks.
Really enjoyed the work. Was thinking about you talked about radial velocity and transits mainly.
Yeah.
And that's the most applicable ones. Thinking about TTVs and also like the shapes of it. You thought about just like the standard deviations in mass and radius. In the work, do you think more about the like the shapes of these distributions, the medians moving around, and then like with TTVs that you can get the mass and radius like correlated, which saves you time on density.
Yeah. Sorry, I didn't hear the question. I'm sorry.
What's the question there? In the work, do you consider some of these the correlation between mass and radius mainly?
No, we vary them both independently. Certainly, I think if you it would probably, if you correlated them, it should drop the uncertainty. It would. Well, I'm not sure because let me move to a figure up here. Yeah. So right, certainly if they're coordinated, I don't think it's going to change our answer all that much. But it's certainly something to take into account. If we know they're correlated, yeah. We kind of treated them both independently because that was the easiest thing to do. But do you know exactly how you would know if they're curved? Or do you have to dig and find that out?
You have to have the posterior. So I talk about it a bit in my TRAPPIST-1 paper.
Okay.
If you want to check that. Yeah. With TTVs especially, you get mass and radius correlated.
Right. Yeah. So I guess, yeah, we didn't dig that far into the literature. We were just we were genuinely curious as to how much smaller error bars needed to be, and it turned into, wow, that's a lot. So yeah.
Daniela, go for it.
Hi, thank you for the talk. I have a question about the sample of your exoplanets.
Yeah, sure.
Can you assume them to be tidally locked? I didn't see, like, just judging from the period, I assume most of them are, right?
I don't know off the top of my head, but yeah, I would say looking at the period, I would say some of them are probably tidally locked. Yeah.
So how do you think that changes, the habitability conditions if they are tidally locked? Do you think that tidally locked planets can be habitable for life as we know it?
Oof. Now I'm gonna take off my astronomer hat because I'm not really an astronomer. I don't see why not. I mean, they're certainly going to have temperature swings from the day and night side. And so in some sense, that's another piece of, if you're worried about target selection, then that might be something you would take into account and throw out some things that are tidally locked. I don't work enough on direct habitability to say whether I think they're habitable or not, but there are probably certainly many tidally locked planets in this sample that we did not take into account because we didn't really need to for the question we were asking. Yeah.
Okay, thank you.
Yep.
Harrison, go for it.
Yeah, thanks, Cayman. It's a really, really cool talk. I don't want to put words in your mouth, but it seems like the statement about you made at the end about going beyond mass radius models and maybe looking at atmosphere observations. Is this a statement about more physics being more constraining? And then, and the example you gave, I guess, for that was looking at atmosphere compositions. I think you mentioned molecular weight. So I'm wondering, could you consider how you could bid these planets by age or something like that? And would that be useful in helping with breaking some of these degeneracies? Or, for example, the sort of related question, the nominal the nominally rocky planet zone. Could you project this over another axis as well, for example, based on galactic evolution, looking at different alpha element abundances? So,
absolutely. So I'll answer your second question first. The NRPZ is based on the Hypatia catalog FGK stars. We currently don't know what, say whether M dwarfs, and most of these, if not all of these planets, are M dwarf planets. If the abundance trends in M dwarfs match the FGK stars, I think they're probably not the same, but it's not enough of a difference to make a big difference for the NRPZ. And then binning by age, absolutely, but that's a habitability question. Well, there's a galactic chemical evolution aspect to it. My guess is it all comes out in the wash, because yes, metallicities are lower in older systems on average with galactic chemical evolution, but the magnesium and silicon ratios are also varying. So in some sense, the ratios don't change a lot. The absolute abundances might, but the ratios might change. I certainly, if you look at my atmosphere, where did I put it? If you look at this paper in AppJ, where we went through the degassing history as a function of galactic time, that will tell you a lot that, older planets are not necessarily great if you're looking for atmospheres. So certainly if you wanted to make a cut on the JWST you'd probably want to look at younger planets because they'd be more likely to have an atmosphere, or at least be able to have retained their secondary atmosphere. So there's all these many pieces in the Venn diagram of what makes an observable and habitable planet. And it's just a matter of sort of picking and choosing which ones matter most. I say, going back to my final figure here, I would say the astronomers care about observability. So all 13 of those planets are observable. You can start wherever you want, but you probably want to go after first the ones where JWST can get done in 10 transits, what would take thousands before. So yeah, I think GCE matters, but it probably matters not for bulk planet composition like iron, silicon, and magnesium. It definitely matters for minor elements, particularly the radionuclides.
That's really useful. Thank you.
Cool. We have a couple of questions in the chat. For those people, if you are happy to ask your question live, you're very welcome to. I'll pause for a second in case you want to jump in. And if not, I can read it out from the chat. Okay, I'll go ahead. So a question from Christine. Does anyone know if these findings can inform the development of the Habitable World Observatory, or are the measurements/instruments already set?
I can answer that. I just sat on an HWO panel about a month ago, and I would say the questions are not set yet. I'm not sure the instruments are set yet, but there's certainly a plan. But we had a really good discussion about this problem. And, certainly one of the problems with direct imaging is that you only get mass. You won't get the radius, or the other way around. I always forget which way it goes. And so in that sense, you can't even do mass radius models. It was one of the inspirations for this paper, is what happens when you can't get the uncertainties you need low enough in a reasonable amount of time. So one of the things we have to think about is, how do you identify a planet as rocky where you only have a direct image and maybe one of the two parameters, mass or radius? So yeah, I think hopefully these kind of things put into context for the astronomers what's important, but we'll see. NASA and will do what they do. Who knows?
Thank you. So another question from Hyang. So for your uncertainty exploration, did you shrink the error bars by a given fraction while keeping the same mean values? Or do you resample your data points with MC or bootstrapping within a certain probability range?
Sure. So I just assumed everything was Gaussian, and I pulled it off of Exoplanet Archive. And it's a really simple, I'm a firm believer in not doing crazy statistics if you don't have to. So from this figure, I let the average vary. So I sampled within the original 3 error ellipse to calculate the different averages, assuming a new measurement will change it. And I know this from experience, having written on TRAPPIST-1 before, that I wrote a paper that was characterizing the interior of TRAPPIST-1, and then 2 months later, the averages changed with new observations. And so it kicked out all my old models were not as useful anymore. So we do let that vary. I don't know if I would call it MC or bootstrapping. It's really just use a Gaussian distribution, produce a million mass radius pairs in their error ellipses to get the new average value, and then slap onto that new average value the uncertainties I'm running for that one. Like, say, I don't know, half a percentage. It's usually I did it in percentages, so 50% smaller error bars. And then I just counted for each individual point, individual M average, I would count what fraction of that measurement landed in the NRPZ. That's it. So it's a dirt simple statistics. I'm sure you could do more, but if anything, it's not going to change your answer all that much.
Fab, thank you. Do we have any last questions in the last couple of minutes? If not, let's thank Cayman again. Thank you so much for a really interesting talk and a great discussion as well.
Thank you.
Before we sign off, a quick advert for next month's talk, which will be titled Climates of Potentially Habitable Terrestrial Planets by Takanori Kodama, and that will be on the 6th of August. More information on the Rocky World website, and if you're not already on the Discord, please do consider joining as well. Thank you so much, everyone. Have a lovely month wherever you are, and see you next time.